Hello, my name is Roxanne St. John, and today we're going to be talking about a universe that I have created completely on my own and has no similarities to our current universe. And any you may notice to a universe, living or deceased, is completely coincidental. You may be asking yourself, why does her microphone never know how to stay on one pitch and just keeps pitching her voice up and down? But you should really be preoccupied with the agenda we have today instead, where we're going to be going over cosmic microwave background properties, early universe properties, expansion history of that fictitious universe, and comparing our data sets with a benchmark universe, which is definitely not ours. It is definitely not the sock's fault. Do not blame the sock. We're firstly going to be going over cosmic microwave background properties. We're going to compare the pattern, power spectrum, graph peaks, and the shape of the universe I created against what information we have with the universe benchmarks comparative of our own to the best of our knowledge. Is it helpful if I get in really close and whisper like this is an ASMR video? So now that the fun is over and we've decided it was definitely not user error, we're going to go over the information that you see in this slide. Starting with the picture in the upper right here, you'll see a graph, or image rather, that looks like a heat map with a line through it where you can see two different images that are quite distinguishable from one another. The metrics for the universe that I created have normal matter, and dark energy all sitting at 0.5. So what this produces when we look at the cosmic microwave background is much larger, more pronounced hot and cold regions than the benchmark that you see in that little corner there. We have these massive explosions of color. We have very deep parts of it as well. So we have high contrast, it's very clumpy. We have a lot of small scale texture as well. So we have a lot of small angle structure that's consistent with the universe that's producing stronger acoustic oscillations. Is this like ASMR? I don't know. I should just drop it, but the reason these are so visually different is because the baryon density that I chose is 10 times the benchmark value, or the value that we consider to be that of our universe, which results in stronger compression, deeper potential wells, larger temperature fluctuations, and that increasing dark matter density also strengthens those gravitational wells. So we're seeing deeper gravitational wells, smaller features becoming more pronounced. And then we have a closed universe, which geometrically magnifies those small angular scales, making peaks shift towards larger multipoles, also known as L. And we're going to talk about that in the next slide here a little bit, but this is just the information about the universe that I made. In this slide, we're going to see if I can get through it without talking with my hands and moving everywhere. So this is the same slide as we saw in the previous, with the benchmark graphs overlaid on top of it with a bit further explanation. So you should recognize in the background the graph that we saw where that peak goes up and beyond and we can't even see it, overlaid transparently enough so you can see both at the same time and lined up as best as I could eyeball, is the graph that we have for our current universe. So our current universe sees its first acoustic peak at an L of around 220, whereas ours is about 234, so a little bit to the right of what we're currently living in. My peak is very tall compared to the standard model, as you can see. And within our current universe, the dampening begins around L equals 1000, whereas, so you can see things kind of start to level out there, whereas my peaks in my graph are still very jagged, still very angular, much more pronounced. When we go to talk about the geometry of the universe, because the total of my three metrics here, the normal matter, and dark energy, total to 1.5, that is the number that is greater than 1. So 1 being a universe that is flat. If it was less than 1, it would have a negative curvature. We would consider that an open universe. And if the number is above 1, we consider that to be a positive curvature, and therefore it is closed. With a closed universe, our light paths curve inward, our angular sizes start to shrink, and as we get those smaller angles, we get those smaller details, we start to get higher multipoles or higher L values. With that as well, our higher matter density that we see in the universe I created shrinks the sound horizon. So, because we have this enormous mass content, the sound horizon at recombination is smaller, then the acoustic scale is smaller. Did I get through this slide without using my hands? No, I did not. We'll put them back down. Thus, we have smaller angular scale and a higher L value. I like to think of L as like the lens. So if I were looking at something very detailed, the larger lens I had, or larger magnifying lens, the smaller details I could see. And my picture is covering up our benchmark, but the benchmark data does reflect a 1 to 0.5 to 0.3 ratio, and those numbers roughly add up to 1, which correlates with the idea that our current universe is flat. Moving forward for a little bit, we're just going to be talking about the universe that I created in the simulation. We're going to be talking about properties of the early universe. So meanings, values, and comparisons of some quantities that I have chosen out of a list. And hopefully we have figured out this mic situation. Maybe if I stop talking about it, you won't notice, but I'm pretty sure your ears already have. I folded the sock over and adjusted the gain on this microphone, and I'm just going to tell you that this is actually meta-commentary on how acoustics work, and it should serve to give you a deeper understanding of the acoustic oscillations at play in the history of our universe and what we recognize now. You're welcome. So we're going to talk about these metrics that I've chosen out of a list. We're going to talk about what they are, and the benchmark metrics, which again are the current universe metrics that we have, and my hypothetical metrics that were derived from the equations that I've provided, and just compare the two. First, we'll start with the baryon to photon ratio. So the baryon to photon ratio essentially just describes how many normal matter particles we have for each photon or particle of light that there is within the universe. The number that I picked at 0.5 is about 10 times bigger than the current universe's number of 0.05. So you can liken this a bit to a soup. Let's say 0.05 is a nice like Campbell's chicken noodle. When you bump that up about 10 times, you're looking at like beef stew from your Nana's house out of the crock pot. It's pretty thick. With that increase in baryons, it's important to note that the number of photons does not change. So we have 10 times the mass, but we have 10 times the matter, but the same number of photons. And this heavier matter content makes acoustic peaks in the cosmic microwave background much stronger. I'm being very gentle because the last time I tried to scroll my notes, it changed the slide. Next, we'll move to the temperature of recombination. The simplest explanation of this is just when the universe chills out enough, literally and figuratively, for electrons and protons to combine into neutral hydrogen. This allows light to travel freely. So can't do it if it's too hot because
they're just running around. They're too hot-headed. They can't have a conversation. They can't sit down at the Thanksgiving table. They got to go cool off a little bit. Too cold, they're never coming back in for dinner. So the temperature of recombination is really when everybody's in that sweet spot and ready to have a conversation. Our benchmark here is 3000 Kelvin, and the hypothetical universe is 6450. This means that the hypothetical universe had to be hotter before atoms could form. The reason for this relates back to our ratio that we just discussed. Because our universe is so much thicker and has so much more matter, it must be much more hot in order for atoms to form, in order to pierce through all of that. So you can see the equation that we use on the right there, where we utilize that n value, and that's how we come to our hypothetical recombination temperature. Again, to summarize, the more baryons we have, the harder it is to keep those electrons free because it's thicker, and so they have a harder time kind of bumping around. It's crowded in there. So recombination has to happen earlier when the universe is still quite hot before it cools down. And what's interesting about that is because it has to be roughly about twice as hot, it has to happen about twice as early. Because these cooling things with the equations that we see, they happen within similar-ish universes. It's an interesting correlation. So the redshift of recombination tells us how much the universe has expanded since the recombination happened. So if it has a higher redshift, it happened earlier in cosmic history because we've expanded more from it. We've put more space between us and when it happened. So because it had to happen earlier when it was twice as hot, it also happened twice as soon. I love when the math gets cute like that. I do. In addition, when this recombination happens earlier, that leads to a smaller sound horizon because things haven't expanded as far, so that sound horizon doesn't get as big, which leads to higher multipoles and shifts those cosmic microwave background peaks. So it's almost like all of these things tie into each other. And then matter radiation equality is one at the bottom here that again was cut off. I'm going to see if I can't move these videos after the fact. But my dogs are being quiet, so I don't think I will have a chance to re-record this. It seems pretty self-explanatory. So this is literally just when matter becomes it. I'm going to use my hands, I apologize. So radiation is dominant in the beginning, right? And then that scale balances out, and then matter becomes more important than radiation for controlling the expansion of the universe. So our matter radiation equality is found right when that little happens, right when they're equal right there. And for us, that is equal to 11,100, and our benchmark is about 3,400, a Z equal to 3,400. So because we have a huge amount of matter, radiation stops being important very early on because there's so much matter, it just takes over everything. Whereas with our current universe, there's not that much, not as much as what I got going on, not 10 times as much. So radiation plays a larger role for a longer amount of time. Do you remember in the 90s and bleeding into the early 2000s where every VHS tape you put in had the coming soon previews that had the same guy narrating every single one that started with "in a world"? just want you to think of him reading the little subtitle above this when you read it. Thank you. So the history and the future of the hypothetical universe in 5 points. I'm sorry. You know, like all of it. Okay, I swear I'm fine. So the redshift that I chose is a z equal to 5,000. I thought it was a good balance between the dark energy dominated future and the equality, which we already determined was 11,100. And that's when matter takes over from the radiation. So this seems to be right in the middle there. Our equation for the scale factor is going to be A equals 1 over 1 plus Z. And so if Z equals 5,000, this is a pretty easy equation to do and determine. The number that we get here means that the universe was only 0.02 its present size. So we're looking at a pretty early stage in its cosmic history. And because it was so early, we can also determine that it was expanding extremely fast. But for the math behind that, we can also use the expansion rate with the matter-dominated Friedmann form. So we can plug in our values for the Hubble constant and set that z value to 5,000. So when you look at the hypothetical equation and the equation column right next to it, these are the same things, just written out differently, so you can see how the basic equation looks with the numbers plugged in, and then look at the results of those numbers. The formatting of the expansion rate in the hypothetical column got a little weird, but PowerPoint was not going to lose when it came to trying to fix that. So just please know that it's 2.47 times 10 to the 10 kilometers a second per megaparsec. So we plug those in and we get that data. So because the matter density is so high, we have this rapid expansion, which also means the Hubble radius was super small, meaning that the universe appeared nearly flat. Our critical density scales as the equations that you see here, and because our critical density of Z is equal to the critical density of 0 times, or at the start, times 1 plus Z to the third, we can flip that around. I'm using my hands again. You're welcome. 1 plus Z times 3 divided by 2. Because the matter density I picked is very big, the matter is the dominant energy component, and radiation only dominated above when Z was 11,100, and the dark energy is negligible when the redshift is that high. And based on the overall density values, my universe is going to just have a great big crunch collapse. And the reason we can tell this is because the total density is 1.5, which we talked about way earlier, and that's well above the flat value of 1, and my dark energy value is 0.5, and that's not enough. The dark energy isn't enough to overcome the matter density, which is the rest of that factor. So that's going to be the 1 of the 1.5. So the matter becomes diluted, and the dark energy only becomes important when that matter's diluted enough at like z equals 0 or negative 0.2, which is so far into the future that it hasn't happened yet in this theoretical Z. So in the long run, as the beauticians will tell you, and South Korean skincare has been long trying to fight, gravity will win, the expansion will slowly halt, and it will eventually reverse into a big crunch type collapse. So what we're looking at here is a very young, very dense, matter-controlled universe, and I could not relate more. So how do we compare when it comes to all the different types of universes and galaxies and supernova that we have charted in the past? As you can see with the star right above my little head, right there, we're nowhere near any of them. Because our data points are matter density being 1 and our dark energy being 0.5, when you plot it on this graph, we are just nowhere to be found. So, yeah, we're pretty out there, literally and figuratively. And that was my presentation. Thank you for putting up with it. I hope you enjoyed it, and hope you take care and don't end up in the cosmic hellhole that I created.